So I will change the moderator. Okay, please.
Hi, I'm Norm Barasa at NERSC, and Shinichi and I are sharing the moderating for this. And I'm in the anchor leg position here for our final three speakers in this last hour that we have. The next speaker, you are all very familiar with, David G, because he's won the award for the most questions asked from all of these events before. Usually held by either Natalie or Jim Rogers in past events that I've been to. He's from Implion, is that how you pronounce it? From Nice, France.
Yes. So I will start short introduction. So my name is David Gulnazaran, but in short, David G. And I'm located in Nice, and my focus on data center decarbonization and heat reuse. And I'm first time on high performance computing conference, but I see real difference when you have co-location data center and high performance computing. It's two different worlds, because in high performance computing, you are focusing on high performance in everything. And I'm happy that now you also start to focus on the data center sustainability, on your high performance computing sustainability. And the message which I want to deliver today is just two main points: what to focus on, what is possible to do, not go many deep details, and make it short to have opportunity to get questions from you to me. Is revenge. Okay, so let's start about environmental and social pillars also for high performance computing. So this is the 6 topics which I will cover really quick. And first question is that already some of you know their carbon of the IT equipment and maybe carbon of the building. And who can say what is the ratio between that? Any ideas, any number from you? What you expect? Yes, we talk about the life cycle of IT equipment and life cycle of the building. And what is the ratio between them? 10:1, okay. Any other suggestion? 2:1. Okay, so next 60 seconds, you will evaluate what is that for data centers, not for HPC, but we can make conclusion after that. So what is the ratio between scope of the building, walls, roof, and etc., and the IT equipment? Let's assume for one rack, we need 3 square meters of space for the rack in front of back. And let's assume that 40 servers in the rack. Embodied carbon for the building, 3 metric tons, for the rack, 40. So, but the lifetime of the building, 30 years, and the lifetime of the servers in the rack, 3 years. And during next 30 years, we will evaluate that the building will remain the same, but the servers turnover will achieve 400. So 400 to 3. It's a 100 time. But the good point about HPC, as we see here, the servers already work for 10 years. It means that it will be not 99 to 1. It will be 33% to 1. I mean, let's say in another way, it will be like 690. So embodied carbon of the servers will be less if you use them as longer as possible. So if you will use them for 10 years instead of 3, it will be like 3 times less. So in HPC, also from other presentation, I saw that the supercomputers which created, they're running much longer than the conventional servers in data center. Now, next one. Next one is to reduce the server's energy consumption. It is possible to do, and I want to show you the comparison of a GPU server, which is one air-cooled and another liquid-cooled. Here, I show the components of the server. The yellow one is the fans, energy consumption in air-cooled version, and orange, it's power supply unit. So when you shift to the liquid cooling, you reduce the energy consumption of the fans, because the red components is GPU, NVLinks, and CPU liquid cooled, and air cooled the rest. And this is why energy consumption of the fans heavily reduced, and that make impact also on the power supply unit energy consumption. This is why we get 20% reduction. So just the way of the cooling of the IT equipment make impact on their energy consumption. Next one. I also want to explain what is mean Impleon. Impleon is mean simple and open, two words together. Simple because if you want to decarbonize that center, you should take away everything which is unnecessary in order to reduce the embedded carbon. And open because open source technologies allow you to drive the innovations. So in this case, I want to show the difference between OCP rack and servers and conventional OEM. So OCP servers reduce the fans in their servers from 6 to 2. And it means that from each server, we take away 4 fans. Another thing is that we don't have power supplies in the servers. The OCP servers are without power supplies. It means that we take away that all the power supplies from the servers. Next thing is that we have one switch instead of 3 in the rack. We take away the PDU because we use one bus bar electrical. We don't need raised floors. Without raised floors, without CRIC units. And in the end, we take away all these components from the rack. This is why it's less expensive and less carbon intensive. Next one is about AI. So here is the NVIDIA cluster with 24 air-cooled racks. And the idea is that these 24 racks can be shifted to the 2 racks with the same amount of GPUs, the same capacity. But in this case, we will have 400 kilowatt in 2 racks. So the question how to make that happen quick, scalable, and the solution is that OCP rack evolution generations. So you will see that here, ORV rack version 3, ORV rack version 3 high performance, and ORV NVIDIA rack. Why it's so? Because in this case, we are able to put 200 kilowatt power supply with redundancy. So on the top, you see power shelves, 4 by 50 kilowatt and below. And between them, 32 6 kilowatt GPU blades, which can have different GPU configuration, and 4 switch blades. So this is the base for the future of AI racks, because that design allows you to achieve the target. And that actually, we already see that new AI racks come with this power shelf and bus bar, and the servers don't have power supply in itself. Another thing which I want to deliver to you, that when you get the server, make sure that the solution of the cooling is the best which you can use. So if you have GPU server with the heat sinks, it will need, let's say, 700,000 liters per minute to cool down them. If you use on-chip cooling with water, you will need around 350 liters per minute per rack. But if you look at the properties of the two-phase, you will see that the difference of the flow rate between the water and refrigerant is 8 times. So AI rack with two-phase will need 44 liters per minute instead of the 350. This flow rate, 300 liters per minute, create conditions when you are not able to put CDU in the rack and you need row level CDU to provide this flow rate per each rack. But with this one, you are able to make rack level CDU, but also there is any details which about how you cool GPU, what temperatures you achieve. So you should understand, is it the right solution which you get? Because you are high performance computing and you can define all the components and choose the best one for you. Even if you use water for the cold plates, you should think about this fluid, because on the market there exist sustainable propanediol PDO fluids which have much less embodied carbon and much less viscosity, which will perform better your pump's energy consumption and the cooling itself. Just for information, what is possible to do. Now about the hyperscalers. So hyperscalers choose OCP approach, and the comparison with traditional data center and hyperscalers, which have OCP servers which can work with 35 degrees water. So the high temperature of inlet air allow you to take away cooling towers and chillers. And you substitute the CRAE units by adiabatic air handling units. Next step is that you don't need UPS, centralized UPS, because on each rack level, you have power supply shelf and you can put batteries exactly in the racks where you need that uptime. And again, as you will grow with these batteries. You don't need to put your investments in advance. And efficiency, of course, much, much higher on distributed power supply than centralized. And another thing that also the IT load itself also go down. Another comparison is about open source modular data centers. So on the left, you see air-cooled open source modular data center. On the right, liquid-cooled open source modular data center for AI. And you see that the same container with air, you can achieve 12 racks with 90 kilowatt. With liquid-cooled for AI, you can achieve 16 racks up to 1.8 megawatt. So the gap is 20 times. The same can be applied for the bigger scale. It's a just example how you decarbonize. So let's say you will have 20 times more performance capacity, but the footprint of the building will remain the same. So also what is important to reduce the energy infrastructure. The ratio between IT load and total power input is very important. And on this slide, I just show that the servers without fans will use less energy consumption. Also, the density per rack can be much higher with liquid cooled. So I show that we're comparing the same amount of CPUs and GPUs between the two solutions, but the rack quantity is less, the power for IT is less, the temperature is higher for liquid cooling. And this is why we don't need CRAE chillers cooling towers, and this is why it reduced from 0.8 megawatt to 0.1 megawatt. We have only dry coolers with the pumps. And uninterruptible power supply units also, they're reduced in the energy consumption as well. So the totally with the same performance, I mean CPU and GPU, we will have 40% less energy infrastructure, 40% less gensets, 40% UPSs, and etc. What it means that if all data center industry will shift from that air-cooled approach to the liquid-cooled, it will allow to grow by 40% with existing limits of the energy from the grid. This is the real decarbonization, when we not grow extensively, but we grow intensively. And about heat reuse. So for heat reuse, we have 3 approaches. First is when we bring data center where is a heat user. Second is we bring heat user closer to the data center. And third one, both at the same time. We can create and data center and his heat reuse application together to fit by the temperatures and by the places and etc. and by capacity. So the data centers are driven financially, and they're looking for the less cost of the land and less price for the energy. And this is why often they're in the middle of nowhere. And when they start think about the heat reuse, there is no one close to them to bring that heat, to connect it and reuse that heat. So this is why we create underground data center, which when we can bring 3,000 racks in the heart of the city by having only small space for the shaft, like 10 on 10 meters, going underground, and under 30, 40 meters, we create the space without disturbing the buildings on top. And by this, we get closer to the heat user without thermal losses, without creating long distance pipelines. And also, we're bringing that center in the heart of the city and solving this issue with the latency and etc. So that is also open source solution which we created. This is how it looks. So we created design when air-cooled racks with backdoor cooling can be really dense. So we use each cubic meter of this space. And you can see how the pipes is placed, heat exchange subsystem, etc. So there is 44 rows, in each row 75 racks. And they're all identical. And the idea is to create design which will be flexible. So you can fill up with just air-cooled racks, like 14 kilowatt, and it will be 1 megawatt for the 75 racks, and shift for the liquid cooling. But you will have the same flow rate, but the capacity will be 3.7 megawatt. And overall, you can shift from 45 megawatt to 162 without any changes in infrastructure. It will be the same heat exchanger, same pumps, same control valves, everything is the same. The difference in temperatures. Next one is subsea cloud. It means that to build underground, you should have the ground quality like in Tokyo or other places where you have metro. If you have metro, then you can build underground. But in some places, and anyway, it will take 2 years at least from design to implementation. With that solution, it was created actually to be closer where you have wind turbines in the sea, where you have subsea cables, and you just making computing. Inside of that is immersion, so we can put up to 4 megawatt equipment in this container. And all the shell, it's not only the space, but also it's work as a heat exchange to make heat dissipation to the ocean or the sea. But another much better application is when you can put that in a river or in the bay close to the city, and take away the heat not to the sea, but to the city. But an implementation will be distributed. It's mean we will not have 45 megawatt or 150 megawatt in one place. It will be 3-4 megawatt, and you connect with the short proximity for the neighbor buildings and provide the heat. But the implementation will be extremely fast. You just put in the water. It will be prefabricated, already designed for the NVIDIA clusters. And by this, you have an proximity and heat reuse and much, much less investments. Because you can imagine this container price will be much lower than any on-ground 4 megawatt installation. Next one is about heat reuse. So in cold countries, you have issue. In wintertime, you have high request, in summertime, no request. In this case, for hot climates, we realized that there is a lot of request for water desalination, and the integration of water desalination and the heat reuse allow you to reduce the costs and operational and investments. But this is a synergy. And a short about seismic activity. So the earthquake make huge impact on the data center activity, but in comparison with the data center here, you can use prevent design that will use no water, waterless, so only refrigerant, and for air cool part and for liquid cool part. And another one is immersion cooling. So I want to show you a short video how it tests. So imagine this is the earthquake, this is the tank, and how you reduce by 95% impact of earthquake on the immersion cooling tank. And what is happening with the equipment inside, because it should be not destroyed, not any impact. And you will see what is happening inside. Because this is the explanation how it can be implemented in seismic activity zones. You see, this is the vibrations, and the 95% of vibrations is taken away just by adding this layer under the bed, small layer. Okay. And the open source approach is that if you have open source service design, rack design, facility design, ecosystem design, then you can look on that, use that, improve that, and contribute for the whole industry. This is all. Thank you for your attention.
Any questions? Now it's payback time for former speakers.
And over the one question, yes.
I've been good all day. I haven't asked questions. So.
Hi, my name is Melvin from Ecolab. I just have something that I wanted to ask and more of a knowledge understanding. So I saw that you share about the container system where you put it underwater.
Yes.
Just curious. So we have been hearing about reducing the water temperature, right? The increased water temperature. So if you have these container systems and the water in the sea or the ocean is supposed to remove that temperature to cool down, would that be an impact? Is there any limitation as to how many containers we can put along the shoreline?
Very good question. Thank you. The idea, as I said, is to reduce impact on the environment. So when we have air-cooled data center, we heat up the air. But that will cost us much more because if air temperature 45 degrees, water in the sea will be 28. And the energy consumption of the compressor with using 45 degrees air will be much higher than by using 28 degrees. Moreover, 28 degrees, we can use like just for cooling. But another question that solution provides you heat in liquid form, which you can use, reuse, make heat reuse. And if you don't need that heat, you don't need to put chillers, dry coolers on the building. You can use just the ocean, and the heat which will be provided to the ocean will able to increase the temperature only by 0.5 degrees, not more. Because the amount of the water, even if it will be the river, the water flow, the surface of it will not able to increase more than 1 degrees. Only 0.5 degrees is possible to heat up. So the answer on your question, how much we can put in the river or in the bay, it can be gigawatts. And right now that project is already implemented for some hyperscalers to provide services for subsea cables, because subsea cables is perfect. You have subsea wind turbines and you have subsea cables. Okay, thank you.
Yeah, quick question. So you've seen at least a dozen HPC designs today, and we are all doing alternatives analysis for what our data center should look like in the future. When should we build a new data center and abandon the one that we're in? So how do you convince us that colo is an appropriate alternative, given that we're on-prem, pry it out of my dead cold fingers, right? I mean, honestly, we are, right? So from an alternatives analysis perspective, how do you convince us, there's lots of big sites here, to abandon what we're doing and move to colo?
To stop you to move to colo?
Yeah. You gave us lots and lots of examples, right, today.
Yes, I'm saying that high performance computing is already shifted to the liquid cooling.
Oh, of course.
And because they understand that it's better for them because they have holistic picture. And I'm just saying for high performance computing, how to be more sustainable, what is possible to do. This is what I show. And of course, the slides about the two-phase, single-phase evaluation, I'm just saying that there is alternatives, how to improve or what to look on in order to achieve better results in decarbonization. But I'm not saying to move to colocation.
Yeah. Okay. All right.
Thank you. Thank you for your question and comment.
All right. In the interest of time, we're going to cut off the questions. Everybody give a good round of applause for David. Thank you, David.